The English Channel is not a static preservation environment. It is a high-energy mechanical system driven by the interaction of currents, tides, and mobile sediment. A few miles off the Kent coast near Deal lie the Goodwin Sands, a notorious shifting sandbank long feared as a ship swallower. This formation is not a solid reef but a dynamic volume of shifting sandbanks that migrate with the tidal cycle. For maritime salvage engineers, the Goodwin Sands represent a paradox. The sediment is soft enough to cushion an impact and envelope a structure, sealing it away from oxygen and trawlers. Yet the environment is volatile enough to scour that sediment away decades later, exposing the preserved object to rapid hydrodynamic destruction. In 2008, a recreational diver noted an anomaly protruding from this shifting seabed. Sonar work and follow-on surveys between 2008 and 2010 by the RAF Museum with partners including Wessex Archaeology confirmed the wreck as Dornier Do A-17Z, Werk Nor 1160. It was a twin-engine bomber lying inverted in 50 feet of water. The sonar imagery was consistent with the high-aspect wings and slender fuselage of a Dornier Do 17Z, later confirmed by follow-on survey work. This specific aircraft, bearing the work number 1160, had been lost on August 26, 1940. In the 70 years since its disappearance, the type had become extinct. No complete airframe existed in any museum collection worldwide. This submerged anomaly was the single surviving example of the flying pencil. The discovery forced the Royal Air Force Museum and its recovery partners to confront a critical engineering threshold. The aircraft was not merely resting on the bottom, it was reacting with it. The primary structure used aluminium alloy skins and internal members typical of Uedico aircraft construction. These duralumin-type alloys can include magnesium among other alloying elements, but the wreck's vulnerability is driven by long-term saltwater corrosion of the aluminium alloys overall. In the early 20th century, this alloy offered an excellent strength-to-weight ratio for flight. In a saline underwater environment, however, it is chemically unstable. The mechanism driving the urgency of the operation was not simple rust, but intergranular corrosion. Over 7 decades, the protective sediment of the Goodwin Sands had shifted. This process, known as tidal scour, occurs when the velocity of water increases as it flows around a seabed obstacle, eroding the sand directly adjacent to the object. The scouring action had exposed the aluminum skin to oxygenated seawater. The chloride ions in the water had begun to penetrate the grain boundaries of the metal, causing the material to exfoliate. The layers of the alloy were separating like damp paper. The structural integrity of key members was increasingly uncertain as corrosion progressed and as the sands alternately buried and exposed the airframe. The engineering assessment was absolute. If the aircraft remained on the Goodwin Sands, the combination of tidal current stress and chemical dissolution would reduce the airframe to a debris field of unrecognizable fragments within a few years. The objective was clear, but the physical constraints were severe. The goal was to recover the airframe intact for stabilization and forensic analysis. This required lifting a structure that had never been designed to be lifted from the seabed after it had suffered 73 years of corrosion. The Dornier Do 17 earned its nickname the Flying Pencil due to its extremely narrow fuselage profile. This geometric feature, while aerodynamic in 1940, presented a catastrophic risk during recovery. The fuselage had a high length-to-width ratio, making it structurally similar to a hollow tube. Under the load of a crane lift, a long, thin tube filled with wet sediment is highly susceptible to hogging or sagging. If the lift points were not perfectly balanced, the fuselage would snap under its own weight before it broke the surface. The recovery team faced a binary choice dictated by the environment. They could leave the aircraft to disintegrate, preserving the site as a war grave until the evidence vanished, or they could attempt a recovery operation that carried a high probability of structural failure. The decision was made to proceed, grounded in the historical significance of the airframe and the technical assessment that a controlled lift was physically possible if the loads were managed correctly. The operation was not a treasure hunt. It was a salvage engineering project operating under strict archaeological supervision and legal constraints. The Goodwin Sands functioned as the primary antagonist in this equation. The site conditions limited operational access to narrow windows determined by the tide and the weather. The depth of 50 feet meant that divers could operate with reasonable bottom times, but the visibility was frequently near zero due to suspended sediment. The current speed across the bank could exceed 5 knots, making precision rigging dangerous and sometimes impossible. The seabed itself was a mobile variable. Between the initial survey in 2010 and the operational planning phase in 2013, the sandbank had continued to migrate. The level of sediment coverage on the wings and fuselage changed with every tidal cycle, altering the weight calculations and the accessibility of hard points. This volatility dictated the pace of the project. The team could not simply hook a cable to the aircraft and pull. Such an action would shear the wings off instantly. The recovery required a custom-engineered solution that respected the fragility of the corroded alloy. The plan required the design of a lifting interface that would cradle the airframe, distributing the tension across multiple verified strong points rather than concentrating it on a single tow hook. The engineering challenge was to translate the geometry of a 1940 bomber into a rigid steel recovery matrix that could neutralize the dynamic loads of the English Channel. The clock was not driven by a dramatic countdown, but by the chemical reality of the aluminum-magnesium reaction. Every season, the airframe remained exposed to the scouring currents. The material thickness decreased. The team established a plan based on the summer weather window of 2013. They had 1 season to design the equipment, mobilize the salvage barges, and execute the lift. If they missed this window, the winter storms of the Channel would subject the weakened airframe to another cycle of mechanical stress that it likely would not survive. The recovery was an attempt to intercept a process of inevitable decay before it crossed the line into total structural collapse. The Dornier was down there, inverted and fragile, held by the friction of the sand and the weight of the sea. The orientation of the Dornier Do 17 on the seabed presented a forensic anomaly. When the survey team analyzed the multi-beam sonar data, the imagery confirmed the aircraft was lying on its back. The wings were inverted, and the cockpit glass was buried in the sediment. This position contradicted the standard physics of a controlled ditching. A bomber impacting the water surface does not typically somersault unless the structural breakup is catastrophic at the moment of contact. Yet the sonar data showed a largely intact airframe. The investigation into the loss mechanics required reconstructing the sequence of energy transfer from 1940 to the present day to understand how a 60-foot airplane could rotate 180 degrees while underwater. The sequence began on August 26, 1940. The aircraft, coded 5K+R, was engaged by RAF fighters over Kent at around 13,000 feet before the forced landing on the Goodwin Sands. The engagement resulted in the loss of both engines and a loss of altitude that forced the pilot to attempt a water landing. The standard procedure for a twin-engine bomber ditching is to retract the landing gear to prevent the wheels from catching the water surface and flipping the aircraft nose over. The pilot executed this procedure correctly. The Dornier made a wheels-up forced landing on the Goodwin Sands at low tide after combat damage. The hydrodynamic loads during the ditching were severe but survivable for the airframe. As the tide flooded the sands, the aircraft became submerged and sank, later coming to rest inverted on the seabed. By the time it was surveyed, the wreck was resting inverted, with seabed movement periodically burying and re-exposing sections of the airframe. The landing gear was retracted into the engine nacelles. The evidence for this initial orientation lies in the preservation of the propellers. If the aircraft had nosed over during the initial impact, the propeller blades would have been bent or sheared by the torque and the collision with the sea floor. Instead, the blades were found largely intact, suggesting they had stopped rotating before the aircraft settled. Contemporary reporting indicates the aircraft sank inverted after the wheels-up landing. Subsequent tidal movement and scour then governed how it was buried, exposed, and degraded over time. The Goodwin Sands are subject to powerful tidal currents that scour the seabed. As the water flows over a resting object, it accelerates, excavating the sand from under the edges of the structure. Over decades, this scouring action destabilized the foundation of the bomber. The hydrodynamics of the wing section, designed to generate lift in air, acted as a scoop in the dense tidal current. Eventually, the destabilization of the sediment combined with the force of the current to roll the entire airframe over. The bomber turned turtle, settling into the sand on its dorsal spine. This slow-motion mechanical event filled the fuselage and wing roots with tons of sediment, effectively anchoring the wreck and shielding the interior from further physical erosion. While the sediment locked the structure in place, the chemistry of the seawater initiated a more subtle, destructive process. The primary threat to the recovered aluminum is a phenomenon known as the chloride trap. This mechanism is the defining constraint of marine salvage conservation. The aluminum-magnesium alloy of the Dornier is porous at the microscopic level. Over 7 decades of immersion, the high-pressure seawater forced chloride ions, dissolved salts, deep into the metal's grain structure. While the aircraft remains underwater, these chlorides are relatively stable because they are in solution. The danger arises the moment the object is removed from the sea. If the airframe is exposed to air and allowed to dry without treatment, the water evaporates, but the chlorides remain trapped inside the metal. These salts then crystallize. The crystallization process exerts expansive mechanical pressure from within the alloy lattice. Simultaneously, the presence of oxygen accelerates the corrosion reaction. The result is exfoliation, where the metal flakes apart in layers, destroying the structural integrity and the historical surface. This is the chloride trap. The act of recovery triggers the destruction of the object unless a specific chemical countermeasure is applied immediately. The investigation of the wreckage also revealed a specific detail regarding the landing gear that confirmed the crew's discipline during the loss. Surveys noted the main undercarriage units were retracted and in place, and reports highlighted that at least one main undercarriage tire remained inflated. More remarkably, the rubber on one of the main undercarriage wheels was reported to be in remarkably good condition, despite decades underwater. In air, especially with oxygen, ozone, and ultraviolet exposure, rubber degrades, but burial in dark, low-oxygen sediment can dramatically slow that process. The persistence of a rubber tire for 73 years while the aluminum alloy around it dissolved highlights the varying decay rates of materials in a marine environment. The final resting geometry of the Dornier was a paradox of preservation. The inversion had protected the upper surfaces of the wings and the cockpit by burying them in the sand. However, this same orientation complicated the recovery. The lift points designed by the manufacturer were on the top of the wings, which were now face down in the mud. The recovery team could not simply flip the aircraft back over without snapping the fuselage. They had to lift it inverted. This required a complete re-engineering of the load paths. The sediment that filled the fuselage acted as a preservative, but it also added unknown tons of dead weight to the lift calculation. The team was not just lifting an airplane, they were lifting a solidified block of sand encased in a fragile aluminum skin. The environment had fundamentally changed the evidence. It had flipped the airframe, filled it with ballast, and saturated it with corrosive salts. The recovery plan had to account for these 3 physical realities. The challenge was to break the suction of the seabed without breaking the spine of the bomber, and then to interrupt the chloride reaction before the air could finish what the ocean had started. In the turbid waters of the English Channel, optical visibility is frequently reduced to less than 12 inches. The sediment load carried by the tidal currents creates a suspension that blocks light penetration, rendering standard photographic surveys impossible for large-scale site assessment. To verify the identity and structural integrity of the anomaly on the Goodwin Sands, the survey team had to rely on a different portion of the physics spectrum. They utilized side-scan sonar to strip away the water column and image the seabed using acoustic energy. Side-scan sonar operates on the principle of oblique reflection. A towfish sensor is dragged behind a survey vessel, emitting pulses of high-frequency sound in a fan-shaped pattern across the seabed. When these sound waves encounter a hard object protruding from the sediment, they reflect back to the sensor. Crucially, the object also blocks the sound from hitting the seabed immediately behind it, creating an acoustic void. On the visual readout, the hard return appears as a bright highlight, while the void appears as a dark shadow. It is this shadow that reveals the true 3-dimensional geometry of the target. The acoustic shadows generated during the 2008 and 2010 surveys were unambiguous. They outlined the high aspect ratio wings and the slender fuselage characteristic of the Dornier Do 17. The resolution was sufficient to measure the span at 59 feet and the length at 52 feet, matching the published specifications of the Z2 variant. The imagery confirmed that the wings remained attached to the fuselage section, a critical data point for the feasibility of a recovery operation. If the wing roots had failed, the lift would require separate recovery of three major components. The acoustic data suggested the airframe was a single, cohesive unit. While sonar provided the geometry, positive identification required physical verification. Divers descended to the site, operating at a depth of 50 feet. This depth is technically shallow, placing it within the range of no decompression limits for recreational diving. But the environment is hostile. The divers worked in near-zero visibility, often navigating by touch. They confirmed the presence of the twin Brahmo 3-2-3 radial engines and the inverted orientation of the airframe. The tactile survey revealed that the aluminum skin was smooth to the touch in some areas, protected by marine growth, while other exposed sections showed the pitting of corrosion. The identification of the specific airframe as Verk number 1160 transformed the site from a generic debris field into a singular historical asset. The Dornier Do 17 was one of the three main bomber types used by the Luftwaffe during the Battle of Britain, yet by 2010 it had become extinct. No intact airframe existed in any museum collection. Thousands had been manufactured and all had been destroyed in combat or scrapped post-war. The acoustic shadow on the Goodwin Sands represented the total global inventory of the type. This rarity altered the risk calculus. If the target were a common airframe, the risk of a recovery operation might outweigh the historical value. For the last surviving flying pencil, the potential loss of the artifact to corrosion justified the engineering expenditure. The depth of 50 feet presented a dual constraint. While accessible to divers, it placed the wreck directly within the high-energy zone of the water column. In deep water, the energy of surface waves dissipates before reaching the bottom. At 50 feet, during a storm, the orbital motion of the waves can reach the seabed, exerting physical push and pull forces on the structure. The survey data indicated that the wreck was not just resting on the sand, it was being buffeted by the dynamic pressure of the channel. The sediment bank that cradled the fuselage was mobile. A shift in the sand dunes could leave the fragile nose section cantilevered over open water, causing it to snap under its own weight. The survey phase concluded with a structural verdict. The aircraft was one piece, but it was chemically compromised. The aluminum alloy was suffering from the intergranular corrosion identified in the material analysis. The acoustic integrity of the wing roots was a snapshot in time. The connections were holding, but the material strength was an unknown variable. The team had proven the identity of the aircraft and mapped its orientation. They had established that the wreckage contained the remains of a significant machine. Now, the engineering challenge shifted from identification to extraction. The physics of the survey proved the aircraft was there. The physics of the lift suggested that moving it might destroy it. The structure had survived the impact of 1940 and the scouring of the decades, but it had no resistance to the point loads of a crane cable. The recovery required a method to neutralize gravity. Engineering a recovery operation is often a conflict between the ideal solution and the possible solution. In the initial planning phases for the Dornier Do 17, the preferred method for extraction was the construction of a sub-sea cage. This plan called for divers to build a steel truss around the aircraft on the seabed, sliding beams underneath the fuselage to create a rigid cradle. The entire assembly, containing the aircraft and the surrounding sediment, would then be lifted as a single unit. This approach minimized the structural load on the airframe, transferring the stress to the steel cage. However, the Goodwin Sands dictated a different reality. By the spring of 2013, the weather window was deteriorating, and the complexity of assembling a heavy steel structure underwater in 5-knot currents proved operationally unfeasible within the available time. The team faced a decision: delay for another year and risk the collapse of the airframe during the winter storms, or pivot to a faster, higher-risk extraction method. They chose to execute a direct lift using a custom-engineered spreader frame. This decision shifted the structural risk from the external cage back to the airframe itself. The engineering challenge lay in the specific geometry of the Dornier Do 17. The aircraft was nicknamed the Flying Pencil for a reason. Its fuselage was exceptionally slender with a high length-to-width ratio. In 1940, this design reduced aerodynamic drag. In 2013, it created a severe structural vulnerability. The fuselage acted as a long, thin beam. If lifted from the nose and tail, the center would sag and snap. If lifted from the center, the nose and tail would droop and shear off. The corrosion of the magnesium alloy meant the skin could no longer carry these bending loads. To neutralize this threat, the salvage team designed a lifting system based on spreader frame geometry. When a crane lifts a heavy object using a single hook, the cables form a triangle. As the hook rises, the cables pull the object upward, but they also pull it inward. This inward compression force can crush a fragile structure. A spreader frame is a rigid steel grid suspended from the crane. It matches the footprint of the object below. The cables drop vertically from the frame to the attachment points on the wreck. By spacing the cables apart, the frame ensures that all the force applied to the aircraft is vertical lift, with zero compressive load crushing the fuselage. The frame effectively functions as a prosthetic spine, providing the rigidity that the corroded airframe has lost. The execution of this plan required divers to attach the lifting cables to specific hardpoints on the inverted aircraft. The team consulted original Dornier manufacturing blueprints to identify the strongest nodes in the structure. These were the engine mounts and the wing roots, where the internal spars were thickest. The plan required the installation of heavy lifting strops around these points. This was a tactile process performed in near-zero visibility. Divers had to tunnel through the sediment by hand to pass the strops around the gear legs and wing spars, ensuring they were seated on structural metal rather than fragile skin. The operational environment added a vertical constraint, the tide. The Goodwin Sands experience a tidal range of up to 16 feet. This massive volume of water moving in and out creates a dynamic vertical target. The salvage barge, equipped with a 60-ton crane, was floating on this rising and falling surface. The aircraft was fixed to the seabed. If the crane operator applied tension while the barge was rising on a swell, the sudden increase in load could shock load the cables and tear the wings off. Conversely, if the barge dropped into a trough, the cables would go slack, potentially unhooking the rigging. The lift had to be synchronized with the precise moment of high water slack tide, where the current velocity drops to near zero and the water level is momentarily static. The pivot from the cage method to the spreader frame method accepted a calculated trade-off. The cage would have supported the entire volume of sand, preserving the context but requiring weeks of underwater construction. The spreader frame required only days to rig but placed the integrity of the fuselage on the line. The engineers calculated that the internal sediment filling the fuselage would act as a stiffener, preventing the thin aluminum tube from buckling. They were betting that the mud inside the plane would provide just enough compressive strength to survive the transition from the seabed to the surface. By early June 2013, the frame was positioned above the wreck. The strops were connected. The system was now a single coupled unit: the barge, the cables, the frame, and the bomber. The physics of the situation were set. The crane would pull, and one of two things would happen. The suction of the seabed would release the aircraft, or the aircraft would break in half, leaving the heavier sections in the mud. The transition from planning to execution meant crossing the boundary from theory to load testing. The flying pencil was about to be subjected to forces it had not experienced since its manufacture, applied in a direction it was never designed to withstand. On the evening of June 10, 2013, the operational phase shifted from static rigging to dynamic extraction. The salvage barge was positioned directly above the target coordinates, stabilizing its position against the 5-knot current running through the Strait of Dover. The crane operator began the tensioning sequence, taking up the slack in the cables connecting the spreader frame to the submerged airframe. This was the definitive test of the engineering hypothesis. The team had calculated the weight of the aircraft plus the estimated weight of the sediment filling the fuselage. But the third variable, the suction of the seabed, remained an estimation. The physics of lifting an object from a soft substrate involve overcoming the hydrostatic pressure differential. When a flat object like a wing rests on fine sediment, it creates a seal. To lift the object, water must flow underneath it to equalize the pressure. If the lift is too rapid, the water cannot penetrate the seal fast enough, and the lifting force must overcome the vacuum pressure of the entire water column. This phenomenon effectively multiplies the weight of the object. For the Dornier Do 17, a rapid lift would exceed the tensile strength of the aluminum skin. The operator had to apply tension gradually, allowing water to seep into the interface between the wing and the sand, slowly equalizing the pressure until the seal broke. The load cells on the crane registered the increasing tension, As the cables tightened, the spreader frame leveled out, distributing the force vertically to the strong points on the wing roots and engine mounts. The structure held. Slowly, the suction yielded. The aircraft broke free from the seabed, rising not as a flexible series of components but as a rigid unit supported by the external steel frame. The ascent was controlled to minimize the hydrodynamic drag on the fragile control surfaces. The inverted orientation, which had complicated the rigging, now proved advantageous. The open wheel wells and the bomb bay faced upward, preventing the fuselage from acting as a diving bell and trapping air, which would have altered the buoyancy calculations unpredictably. As the spreader frame broke the surface of the English Channel, the wreckage of Werk number 1160 became visible for the first time in 73 years. The transition from water to air is the second critical danger point in a recovery. While submerged, the aircraft benefits from buoyancy, which supports the weight of the structure. As it exits the water, that support vanishes instantly, and the effective weight of the airframe increases. Furthermore, water trapped inside the wings and fuselage must drain rapidly. If the drainage is blocked, the trapped water adds tons of static load to the structure, potentially causing the wings to shear off at the roots. The drainage holes functioned correctly, and the water cascaded from the trailing edges as the crane hoisted the bomber clear of the swell. The visual condition of the airframe validated the forensic predictions of the survey team. The aluminum surfaces were heavily encrusted with barnacles and marine concretions, confirming the biological activity of the site. However, amidst the gray and brown tones of corrosion and decay, one component stood out with anomalous clarity. The tailwheel, still retracted in its housing, was intact. More significantly, the main undercarriage tire visible in the inverted nacelle remained inflated. This detail, seemingly minor, provided a specific insight into the preservation mechanics of the Goodwin Sands. Rubber is an organic polymer that typically degrades when exposed to ultraviolet light and oxygen. However, the tire had been buried deep in the anaerobic sediment, shielded from the sun and the oxidative environment of the open water. The pressure of the depth had balanced the internal pressure of the tire. Its survival was not miraculous. It was a predictable outcome of the specific burial chemistry. The tire offered a stark contrast to the surrounding metal. The rubber had survived the decades better than the magnesium alloy. The crane swung the load inboard, lowering the cradle onto the deck of the barge. The airframe settled onto the pre-prepared cushion of the transport mount. The recovery team conducted an immediate structural assessment. The fuselage had not hogged or sagged. The wings were still attached. The propellers, although bent from the initial ditching in 1940, were secure on their shafts. The spreader frame concept had worked. The geometry of the lift had successfully neutralized the fragility of the flying pencil design. The successful recovery of the Dornier marked the completion of the extraction phase. The objective defined in the claim ledger, to recover the airframe before it collapsed, had been achieved. The operation had navigated the constraints of the weather window, the tidal range, and the material degradation. However, the physical recovery created a new, immediate crisis. For 73 years, the aircraft had existed in equilibrium with the seawater. By removing it from the ocean, the team had broken that equilibrium. The airframe was now exposed to the atmosphere, and the chloride ions trapped within the metal began to react with the oxygen. The timer had reset. The mission shifted instantly from a mechanical salvage operation to a chemical stabilization emergency. The aircraft was safe on the deck, but it was already beginning to die. The recovery of the Dornier Do 17 from the seabed did not mark the end of the engineering challenge. It marked the beginning of a chemical siege. The moment the airframe broke the surface of the English Channel, the protective equilibrium of the underwater environment was shattered. The aircraft was now exposed to an oxygen-rich atmosphere, the catalyst required to activate the chloride salts embedded deep within the aluminum alloy. If the metal were allowed to dry, these salts would crystallize and expand, shattering the remaining molecular bonds of the structure. The exfoliation process would accelerate from a geological time frame to an immediate crisis. The team had a window of hours, not days, to establish a new artificial environment that could arrest this decay. The aircraft was transported by road to the Royal Air Force Museum at Cosford. Upon arrival, the fuselage and wings were not placed in a hangar but inside two custom-fabricated polytunnels. These structures functioned as large-scale hydration chambers designed to maintain a specific relative humidity and temperature. The preservation strategy relied on a process of continuous chemical irrigation. The objective was twofold: to soften and remove the dense layer of marine concretions obscuring the surface, and to flush the chlorides out of the metal grain structure. The weapon selected for this chemical warfare was a low-concentration solution of citric acid. Unlike harsh industrial strippers which might dissolve the fragile magnesium alloy along with the rust, citric acid offered a controlled reaction. It was aggressive enough to break down the calcium carbonate of the barnacles, but gentle enough to preserve the aluminum substrate. In purpose-built hydration tunnels, the aircraft was systematically sprayed using a low-concentration citric acid-based solution to soften marine accretions and support corrosion impurity neutralization. For months, the Dornier lived under a perpetual acidic rain, keeping the surface wet and facilitating the ion exchange required to neutralize the salt. This phase of the operation revealed a non-obvious technical complication detailed in the engineering logs. The interaction between the citric acid and the organic biological matter decaying on the airframe produced an unexpected byproduct. As the barnacles and marine growth dissolved, they reacted with the acid to form a viscous sludge with the consistency of agar gel. This gelatinous substance washed off the airframe and entered the recirculation system, where it rapidly clogged the filtration units and seized the pumps. The conservation process threatened to choke on the biomass of the Goodwin Sands. The engineering team was forced to redesign the filtration architecture, installing coarser primary screens and high-capacity pumps to manage the heavy organic load. It was a reminder that the aircraft was not just a machine, it was a biological host. The hydration process was not a quick fix, it was a discipline of endurance. The initial spraying, soaking phase ran for well over a year, before later stages shifted toward longer-term environmental control and continued treatment. Following the citric acid phase, the treatment shifted to other inhibition agents to stabilize the surface permanently. The goal of this extensive effort was never to restore the Dornier Do 17 to flight condition. It was not even to restore it to a pristine static display standard. The philosophy of the project was forensic preservation. To replace the corroded skin with new metal would be to erase the history of the object. The damage, the bullet holes from the intercepting Defiance, the bent propellers from the ditching, and the corrosion from the ocean, was the evidence. Today, the aircraft exists in a state of arrested decay. It is displayed in a climate-controlled environment that prevents the reactivation of the corrosion cycle. The success of the operation is measured not by the gloss of the paint, but by the stability of the structure. The recovery proved that it is possible to retrieve a large, fragile composite object from a high-energy tidal environment and transition it to a stable museum setting without catastrophic loss. The Dornier Do 17 serves as the only physical reference point for a type that once numbered in the thousands. The legacy of the project lies in the geometry of the lift and the chemistry of the tunnel. The engineering team proved that the flying pencil could be held by a spreader frame without snapping. They proved that the chloride trap could be defeated by a lattice of 36 nozzles. The aircraft remains a wreck, but it is a stable wreck. It stands as a testament to the violence of 1940 and the technical discipline of 2013. The ocean took the bomber, hit it, and broke it, but the engineers refused to let it finish the job. The dissolution has been halted, the evidence is locked.